Okay. Okay, so let's wrap up our intro to MATLAB workshop. We're gonna continue with looking at the data that's coming from one of the papers reporting protein expression data. So this is gonna be the same data set as yesterday. I just trimmed it, so we're not gonna run into problems with the memory on the laptop, which is not the best in the universe. As a reminder, the data we've got is reported for several experiments. We're gonna have 150 or so columns of data. Each column describes a change in expression data of one of the about 3,000 genes that were measured either in a wild type unmodified version of yeast or yeast with one of the genes removed. So this tells you how sensitive each of those 3,000 genes is to deletion of knockout of one of the other genes in yeast. And the question is how to find something interesting about the data there. To do it, we're gonna go back to MATLAB. Okay, let's get out of my slides. Let's hide it here and let's go back to MATLAB. Let's go on here. Here we go. Okay, so the data set is as yesterday on a Google Drive, so you can download it and play along with whatever I'm gonna do on the screen here. The file for today is the one here, and it starts with the recap of whatever was done yesterday. So we initially imported data. This is hopefully by now a standard recognizable procedure. I'll clean up the workspace so there's no background. I clean up just in case the command window, and then once we do Control Enter to run a block of code, here's our data. Here we've got about 3,000 individual genes characterized in about 150 experiments. As the data file that we're reading is composed of both columns that contain numbers and text, when import data runs and returns a piece of data structure that has two parts. There's a part with the numbers. This is this .data part, which is saved into ed, and then ed variable is just a conventional array in MATLAB. We can check at the top left corner of it. If you check ed, let's say 10 to 5, 1, 1 to 5, 1 to 5. This is what's there. There's just a corner of the big matrix. In each column corresponds to a different strain where one of the genes was knocked out. Each row corresponds to a gene that where its expression was measured across all the experiments there. To find out what those genes are and what the experiments are, we can use the other part of data, the text element of the data structure, which I wrote to ET. We check what's there. There's going to be, as we see here, there's going to be a set of columns, two columns with either systematic name or stand or oh, there's something bad here. Well, or it's gonna be, I think, once more systematic name of the gene, and then along the top row you've got the names of the genes that were knocked out in each experiment. So this is what we had yesterday, and that's what we're looking at for a while. Okay, so we started with converting the raw numbers that came from the data to make them comparable between experiments. To do this thing, I have calculated, and this is pretty common procedure. I have calculated so-called z-value or z-score, which is essentially normalized, essentially the value of expression that's normalized, so that our entire data series, as on average, has a mean value of 0 and standard deviation of 1. To do this thing is we can just calculate the mean of our data. As a reminder, if applied to an array, the mean function calculates averages for each column. So it means that if we calculate mean of ED, and let's try it here. If we calculate this thing, well, I can calculate up. Yeah, let's calculate it here. Then, as you see here, we're getting a vector or an array with one row and 150 columns. So this is gonna be an average for each of the 150 experiments, average change in expression for all those experiments. If we want to see what's in this variable, we can use the workspace and plot, for example, look at the histogram of the data. And this is distribution of the averages. Most of the data sets are centered at 0. Some of them are shifted out. To make all of them comparable, we can subtract the average value from each value from values for each experiment, and then the average is going to be set to 0. That's what's done here. We can copy and paste it and run it in a console. Yeah, no, it doesn't work. That so we can okay. So now we subtracted the average value for each data set from the data points from this data set. This is how subtracting or doing plus minus operation on a matrix and the row vector row array looks like. If we check the size of ED variable, this is 3000 rows, 150 columns each row. If we check our average, this is 150 rows, 1 column. When we execute the operation here, MATLAB is gonna take each row of the ED matrix, gonna subtract from each element by element the values in the average, and then it's gonna do it for a second row, third row, fourth row, and so forth of the ED matrix, and it's gonna return the result. So if we run it now, so if we actually run this thing, we didn't so far. Here's our E1 matrix, and now if we let's say calculate, we can calculate for this thing for E1 average, we can calculate mean of E1A. This is gonna be our average or mean value for the initial data after subtracting its mean. If we do this thing, if we do E1, sorry, E1, okay. So now if we check what's E1, if we plot the histogram of averages here, we should get things that are very close to zero. Yes, there's some difference, but this is minuscule. Those are random errors. Computers can't operate on numbers with arbitrary accuracy, so there's always some random error, but that's really tiny. So we corrected for the shifts from the average between data sets. And once we did this thing, we can also calculate standard deviation for each column. That's how it's done here. That's how it's done here. Control V. We can save the standard deviations. So we can check if we're interested how they look like. Here's we can plot the histogram of those. Yes, they vary. Most of the standard deviations are somewhere around 0.2, but there are a couple of data sets with much higher variability for the between protein expression. So to correct for those, we can just take the value that we stored in a ESTD array and then use it to divide the values in our initial our corrected data sets, the corrected values in E1. This is after subtracting averages. So now if we calculate if we divide our data values by the standard deviation for each data set, we should get the standard deviation normalized to 1. Thing to pay attention to is that here I'm using a dot version of division. This is because I want to divide the values in E1 the same way as I subtracted standard deviations. I want to do it element by element, and this is how the dot slash operation is defined. If I were to use the slash operation, this would be actually a vector operation. The result would be completely different than whatever we're expecting. We can do it, it will work as far as I can tell. We can do it, but the result is not what we expected. We expected to have as the result a matrix once more with 4,000 rows, 3,000 rows, 150 columns with corrected data. If this division doesn't do it, it generates one-dimensional fixed window. I'm not sure if can I fix the window of figure? I'm not sure. It might be possible to paste it into GUI, but I'm not sure if this thing can be done. I mean, normally if you've got a big screen, it's not a problem. You can shrink the MATLAB window and have those two things overlaid. So this is one way I didn't delve into details about the window. So I can try to find it, but it's maybe it's possible. Okay, so as you see, the slash operation generates a vector. It's essentially solving a vector equation and or matrix, the linear equation, and then it spits out result in a easy. We want to do something different. We want to actually multiply elements of E1 by whatever is in the STD. To do it, we use dot slash. We click here. Now our EZ looks like as it should look like. We can now just check what's the standard deviation of our EZ data set is. To do this thing, we can calculate, let's say, EZS, which is E1, which is gonna be EZ, and it's gonna be standard deviation of our EZ, STD. And then when we check what's in EZS once more, we can get the histogram of it. And here, everything is equal. We're getting a very flat, everything goes to 1. So this way we normalize data to standard deviation equal 1, and the average value for each series set to 1. So another, well, so now once we've got, here it's done in several steps. I essentially calculate separately and store separately an array with averages. Here I'm getting standard deviations, and then I'm doing math one step at a time. Everything can be compressed into just one operation. This is exactly what's happening there, except that I just put everything into single expression. We can do Control C, Control V, this thing, and we're getting the same thing. If we check histogram of the corrected, well, that's easy. So this is not it. It's in this one here. Okay, so this is how to calculate calculate this course just in one line. This is pretty simple in MATLAB. In most of the languages, you'd have to do explicitly all the math by looping over individual values in data sets, and then do the math on your own. Here you're getting this thing in a pretty rapid way. So that's how to normalize the data. Once we've got it, we can look at it, and it show you how to get the histogram of the data. That's right. If you want to do it from a script, you just execute the command like here. If we run it, here's a histogram for the 50th column of the data. This is because I specified that I want that from the AZ variable, I want to take all the rows at 50th column. If I want to change it to column number 30, column number. If I want to change it to column number, let's say 33, I can run it, and we're most likely gonna see something different. Yes, it's different. Apparently, there are a few outliers all the way on the left side, which make the MATLAB to show the axis extended further to the left. You might have noticed that the plots we're getting here are interactive. So if you want to zoom in, you can just zoom. You can either let's get out. Let's go back. The home resets everything. If you select the hand, you're gonna be able to drag things around. If you want to zoom in, I think dragging, you can stretch a marquee and look at the details. So if you want to zoom out, you can click on this thing. So the graphs here are interactive, and I'm not gonna go over this thing, but there's a lot of options here. If you check those things, you'll discover that it's possible to edit what you see here, annotate, add your own scribbling. So a lot of things can be done from the panel here. I like to cover just the scripting part of the graphics. So I'm gonna skip the graphic, the interactive part for you to discover. It's fun to play with it. Okay. Now, well, if you want to customize what you see from the script, you've got to assign whatever the call to the histogram function returns to a variable, and then you can change properties that are there. They are going to be different between different types of plots, but in case of histogram, one of them is normalization, and there are several options there. I'm setting it to PDF, which is probability density function, which essentially normalizes the area covered by the histogram to 1, and apart from that, I'm setting the title of the histogram so that we can annotate different histograms, different plots with the title. If we run the entire block now, here's a histogram here. Now it's presumably normalized to maybe it is, maybe not, to area 1. It should be. No, it doesn't look to me like it is, but well, maybe. And we did set the title. This is the effect of what we did here. Okay, there are other properties that you might be interested in or might find useful. To find them, once we've got a variable with which points to a given histogram, we can just type it in a console, and if it happens that histogram is gone, there's nothing there, so you can't do anything. So we've got to rerun our exercise. Okay, and then you can go here and print what's in H. We're gonna see a few useful properties. The one I've used was normalization. Another one is the color of the bars in the histogram and the color of the edges, which can be modified. In both of the cases, the colors can be changed by saying edge color, and then now without typos, hopefully, and specifying that we want to set it to a color which is specified as a red, green, and blue value between 0 and 1. 0 means the color is turned off. 1 it means it's fully on. If all three values are set to 1, you're gonna get white. You're gonna have all the values set to 0, it's gonna be black. If you want to make edge colors, let's say in green, you can say 0, 1, 0. Okay, and then once we do this thing, the edges of the histogram turned green. It doesn't show up too well now, but we can always zoom And here are the green edges. If we want to make the face of the bars also green, we can say H, face, and set it also to green. And then we've got everything green here, or we can set it to all zeros. We can set the edges to zeros, and then we've got the black outline around the edges. So we can also set the title, as you've seen, by specifying title in a special separate call. What we can use with the histogram itself, we can change normalization. We can look what's there. If you do H, or then we can do PDF. This is our initial value. Okay, so this is not gonna go not this way. Sorry, I'm confusing things. For the properties, you just assign a value to the property. Here we go. This didn't change anything because this was our starting point. I'll just reset the view. Okay, we can set this thing to count. Think we do it. No, count without S. If we set it to counts, then we're gonna have the actual number of observations falling within the range corresponding to each bar. Another option is probability. This is gonna be the fraction of the samples falling within each bin in a histogram. PDF corresponds to this fraction, but in a limit where the width of the histogram bar gets to, the width of the bin goes to 0. CDF is another useful thing. It's if we set it CDF, and if we set it, then it's gonna look like this. So this is adding, this is cumulative distribution. This is this is probability that or the counts being added up. So the sum of the counts starting from the leftmost bin all the way up to the rightmost, they add up to 1. So this is essentially the y-axis. Tells you what's the fraction of observations below a given value on x-axis. At 0, half of the observations are already past the cutoff. The other half of the observation should be above 0.5. So this is a different way of looking at your data. Okay, so those are histograms. Another useful way or informative way of looking at the data are so-called box plots. They are also easy to use. You can just say, as you see here, that we want to look for or create a box plot. We're gonna use our data. We're gonna use all the columns and all the rows, and we're gonna look at first 5 columns. So if we do it, Control Enter, then we're getting a slightly different show. There are 5 box plots because there are 5 columns that we are looking at each box corresponding to one of the columns, one of the experiments. If we zoom in, let's say here, we're gonna see that. Let's drag it sideways. We are getting in the center and the zero and median. This is the value of the median. So this is the value where half of the data set our data set is below the median, the other half is above. So for all, after normalization, this thing should be zero for or close to zero for most for our data sets. The box covers the range of values here that covers the range of values that corresponds to half of the data points. Upper half and lower half corresponds to 1/4 of the data sets. The values diverging most from the median are corresponding to values that are either above, this is the top 1/4 of the data, and lower 1/4 of the data. The whiskers, the horizontal lines and dashes correspond to whatever is considered to be non-outlier data. In practice, it means that this is roughly 3 standard deviations from the mean, and things that are different than 3 standard deviations from the mean are shown explicitly as separate crosses here. So this is another simplified way of looking at 3,000 or so points and data points at the same time to see something about how they're distributed. So that's the box plot, and as you can see here, generating plots for more than one series is slightly easier than with histogram. With histogram, we're getting one histogram at a time. Here we can plot more data sets all at once. So that's something new compared to whatever we did yesterday. But going back to whatever we did then, I did show you that you can, in principle, try to fit the normal distribution to your data using the norm fit function. It's gonna take as an input one of your series, return the mean value and standard deviation of a normal distribution that would be best to describe your data. In the case of this course, it's relatively boring because you're gonna retrieve essentially the same average value and standard deviation 0 and 1 as we normalize the data set to. So for normalized data, this doesn't generate anything interesting, but for unnormalized data, it would be different. Okay, and if we want to actually plot the expected distribution, the expected normal distribution on top of our histogram, it's sort of messy, but it's got to be done in steps, but it's feasible. Okay, here that's what I've shown yesterday. We essentially, starting with setting the hold to off, it means that the next drawing operation will erase the previous stuff in our figure, so that we clear the screen or our sheet of paper where the drawing shows up. We then plot the histogram same way, normalized to as PDF. Okay, so this part generates the histogram. Okay, now we're picking up a range of values. Here I've decided that I want to go from -5 to 5, about that's a wild guess. It can be done better. You'll see just in a moment. And then I just printed out or calculated the value of the normal distribution normalized as PDF for a standard deviation of 1 and the mean of 0. This is what our data sets were corrected to. So that's how they should roughly look like. Okay, and once we've got our range and values to plot, then we set hold to on. This will make MATLAB to actually plot on top of whatever is already there, so on top of the histogram, and then at the very end I'm setting it to hold off, so that we're back to default, so we're staying. So the next plot, if it happens, will not override whatever we've got here, but it's gonna start from a scratch. If we run this snippet of code, we should see our histogram as before, corresponding to, in this particular case, our 50th experiment, overlaid with the normal distribution with the same width and same standard, same mean. Apparently the data is not distributed according to normal distribution. Is much slimmer. Well, that's not exact. Well, it's got much wider wings on the side that make the standard deviation look bigger than expected. So those two distributions are clearly different. It's gonna be varying from one experiment to another. It's sort of informative to look at those things and see how each experiment looks like. The problem is, it's sort of tedious. We can start by putting together more and more histograms on one page by hand. To do this thing, we first got to divide our page into grid of plots. That's what it's done here. We're specifying that I want to make a grid of 3 columns, I mean of 3 rows, each with two plots. Okay, and I'm gonna start with plotting in the first position, which is gonna be top left corner. So this is first row and first column. I'm gonna plot histogram corresponding to position, let's say 50 for the 50th experiment, and then I'm gonna hold on, plot something on top of it. Then I'm gonna switch to the second position in a grid, which happens to be the first row but the second column. So the filling in the grid goes on a row by row basis. And we plot another histogram, we hold on to it, we plot another normal distribution, then we switch to the third one and so forth, and we can run this thing. Okay. And we're getting partially finished grid. This is our first subplot, second, third, and the fourth one will show up here, 5th and 6th. So that's how it goes. It can be done by hand, but this is tedious. This is tedious and error prone, and then every time you change something you want to plot, you have to find where to modify things. So for this type of operation, this type of code, it's better to convert what we've got here into a more generic function. Okay, and that's what I was starting yesterday at the very end of the day, and I ended up with a function that looked more or less like here. I can open it in a separate file to see what's there. Okay, so this is how a user written function looks like. It always resides in a file that's named the same way as the function name. Okay. To denote that this file contains a function, we've got to start it with the word function. And if function returns a number, returns a value, then we specify a variable here, which it's gonna be returned by the function if needed. If the function does only some graphics operations, nothing else, we might not need it, but sometimes it's useful. So I left it here. And then after the name of the function, there's a list of arguments. The first one is gonna be the data set we want to look at. Then there are going to be two numbers specifying how many rows and how many columns we've got in our panel of histograms. Then there's gonna be a list of columns that we want to show in each of the panels. So it's gonna be set to a series of numbers, each one telling MATLAB which column in data to plot. And then finally, there's one more parameter to set up the height of the histogram. What's the range of the y-axis? So it seems to be pretty useful, and you might want to have a way of controlling it from outside. Okay, the way this function is called is clearly visible here. Here is our data. And then we're asking for a panel with 2 rows and 2 columns. We want to plot there the first, second, third, and fourth data set. So those are the 4 columns of ED that we're gonna plot, and we want to say plot each histogram with covering the range of 6.5 units or something like that. Whatever's gonna look good. Okay, so once a function like this is executed, MATLAB goes to this file, starts to run the code here, and it essentially here starts with setting up a figure that our plot is going to show up in. This is figure 1. So we don't have a panel, so this is going to be the window named figure 1. We can specify, once we save what figure 1 returns, we can specify where this window is going to show up. This is coordinate of the left, of the bottom left corner of the window. I'm setting it up to 50-50, so it's going to show up somewhere down in the left corner, lower left corner of the screen. And the window is going to be 800 by 600 pixels wide. So this is how you control how the plot shows up on the screen. It's if that's what you like, it's fine. If ultimately the windows got to be resized, you can modify it from the graphical user interface by scaling the windows, stretching, whatever. But those are the initial settings. I'm also setting up the background color for the panel. In this case, it's something that's gonna pretty light with a little bit of bluish green tint. So the same idea. You set colors by passing an array with 3 numbers corresponding to red, green, or blue. If you don't like it this way, you can check documentation. There's gonna be a list of colors that you can pass as a string, so you can say explicitly red, green, blue, magenta, and a bunch of other things, and you can use it this way. So there's more than one way of specifying color. And finally, I'm setting up the name of the window to histogram panel. Okay, once I'm done with setting up the global settings for our plot, our panel that we're generating, then I'm going over something that happened. I'm going over the columns. That's right. I'm checking what's the length of the column variable that I passed here. This is the one that contains, in this particular case, 4 values, 1, 2, 3, 4. I can make it something else. I can make it 11. Let's say I can make it 21, and I can make it 44. Whatever it happens, we're interested in. Okay, so those values will be passed as the calls parameter. So this is gonna be an array with four values. I'm going over those 4 values one at a time, and each pass through the for loop, PP is gonna be set to one of those values, and then I'm using the PP value to get hold of the particular column I'm interested in. So here calls PP evaluates to the number of one of the columns I'm interested in, and I'm getting entire column, all the rows in this column assigned to P data. I'm checking for the max value and the min value of the data points. Okay, this is to set the width of to set the range of the x-axis. Okay, now it's reasonable to have some extra space below and above the maximum value. So I'm setting the minimum value on the axis to be the value of minimum value of data less 1/10 of the range between minimum and min and p, not min, p max, max, and same thing here, p max. Okay, so the data covers the range between P max and P min. I'm gonna use 1/10 of it to extend our axis to the left below the minimum value, and extend it by 1/10 of it to the right of the maximum value. Okay, so those are our values for the range of along the x-axis. I'm gonna now specify that I want to work with the subplot with a grid of n rows. This is what I passed. This is what was passed here as a number of rows, and this is number of columns coming from another argument. And this at each pass, the PP is gonna specify which panel I'm gonna fill in. So I'm gonna be filling in the same way as you've seen before, done by hand, by filling in the top left corner, one position to the right, another, as far as there are enough columns in a grid, and then we'll switch to next row and so forth. So that's the order of filling in the grid. Once I'm in the subplot, I'm gonna set hold to off to make sure that nothing there is present. I'm gonna plot the histogram using either data directly as it was passed here, or I can use the P data. In principle, I can just use the value here. P data is the same as what we've got here, so I can simplify this thing a little bit and say that I want to plot the histogram of P data. Okay, once I get the handle of the histogram, I can set normalization that I want to use, and then I can specify that the axis for our plots are to be from x min to x max for the x-axis, and then from 0 to y max that I specified as the last argument to our function here. So that's what we've got here, just to set the axis. So that's all what our function is doing. I think I should add another end here because I'm missing it. The block that's repeated within the for loop should start with the for statement, and then there should be end denoting end of the loop, and then there's finally the end to mark the end of the function. Once function, I modified the function with a star here, so there were modifications here. So I'm gonna save this file. Okay, and then I'm gonna go back to our code and see what happens if I call it. Let's see here, and here is our plot. Note that I was using the raw data, the data that came directly from experiments. So that's why the data is not as is not wide to the same extent as before. Plus, there are outliers in the different data sets spaced either further on closer together. So the ranges for the x-axis vary quite a lot between the plots, but we do have the same 0 to 6.5 height for each of those plots. If we want to change the height, it's easy. We can just say we want to plot, let's say, up to 5, and if we want to change the data sets that we want to show, we can change it here, or we can even add another. Instead of plotting 4, we can plot, let's say, 1, 2, 3, 4, 5, 6, 7, 8. The first 9 of those, but we'll plot them in a 3 by 3 grid. Okay, and this way, if we run the code, we should see now we should see now 9 panels, each for a different data set. This is going to be first one, second, third, fourth, and so forth. So this is a way to deal with generation of panels of histograms or other types of data. With a little bit of extra work, those functions can be modified. They can be more customizable to more extent. I do have another example of the function here, but we'll deal about it after a break, after when we start to deal with the conditional statements and making programs do different things depending on what we want to make it do. So for now we'll have a break for, let's say, 5 minutes. So I'll stop the recording. Come on. Recording. More. And we will be stop, cancel, pause, not stop. Go on. Okay. I tried to check if it's possible to fix the figure window as one of the panels in GUI, but it doesn't look like it is. Maybe, but I'm don't think so, because as you've noticed, every time you generate a figure, the panel pops up on its own. So I don't think so, but it might be possible. It's a matter of matter of googling around. Okay, back to our data. Okay, so so far, whatever operations I was performing, they were done in they were performed all the time. So all the scripts I had, they were running the same code. I might have read a different data, and if I wanted to change some of the parameters in a systematic way, I was running a for loop with parameter, like here, changing a systematic way from one pass-through loop through the other. In many situations, you want to actually make decisions based on your data that you're dealing with, and you want to do different things depending on if data is above zero or below zero, or some other parameters. To make decisions, first you want to be able to compare different things, and this is what conditional statements are about. Okay, first we want to be able to compare things. Let's see. So let's clear the command window, and the simplest thing you can do is you can ask MATLAB if 1 is greater than 2. Okay, and if we check the answer, as a reminder, if there's no semicolon, the result is printed out in the console. If there's semicolon, it doesn't show up here, always shows up in the workspace. So you can check what's the result here even without cluttering the command window. And the answer is either true or false, depending on if this condition is how this condition evaluates. In this case, 1 is greater than 2, so we should be able to get. Why are we getting 0? That's interesting. Oh, that shouldn't be the case. I'm puzzled. Okay. Well, we'll see. Oh no, 0 is true apparently, and if we flip, okay, we do 2 is greater. Oh no, well, it is false. 1 is less than 2. Yeah, 1 is not greater than 2, so this is not true. So we're getting 0 or logical false. And if we flip the sides, if we check if 2 is greater than 1, then we get logical 1 or true value. So that's how you compare numbers. You can use other standard comparison conditional statements. You can check if a value is greater or equal to another one. Well, this is true. If same is gonna be here, it's true. If we go to 3, this is false. So there's an entire series of operations here to compare if two numbers are equal. If you use double, you use double equal sign. So you've got to do it like this. It's duplicated because otherwise it would be confusing. It would look like an assignment statement, and this is important because the arguments on both sides of the comparison operators of those operators, those could be actually variables, not only fixed values as here. So if we have, let's say, a number stored in variable k, let's say 4, then we can check if k is equal to 4. Yes, it is. Is it equal to 2? No, it isn't, but we've got to make sure that we use an duplicated equal sign. If it's single one, then this thing would be interpreted as assignment. So now what we've got in k is, we didn't check if k is equal to 2. We checked if we put the value 2 into variable named k. So that's why equal comparison is composed of two equal signs. If we want to check if something is different, then instead of the first equal sign, we use a tilde. So if we want to check if k is different from 2, we would say k tilde 2, and this should evaluate to false. Yes, that's what it is. The nice thing, yeah, if we've got a more complicated situation, we might want to check if variable k is equal to 0 and variable L is equal to 2 and so forth, then we can combine those imperial conditions with using logical operators. If we want to check if, let's say, k is greater, let's say, greater than -2 and at the same time smaller than 2, we would say that we would check the first conditions and k is less than 2. Okay, and then depending on what we've got stored there, I'm gonna get either true or false. If both sides of the AND operation and AND operator are true, then the resulting value will be set to true. If not, then if either of those conditions is not fulfilled, then you will get a logical 0 or false. So this is the case here. So that's the idea for comparisons and logical operations. And most common place you'll find them, or at least one of the places you will find them, are so-called if statements. Here's an example. We initially generate some sort of a test data. So here's something that the code is generating. MATLAB is in general very nice in terms of you being able to generate copious amounts of test data of various sorts with barely any thinking at all. Here, what I generated is I've generated a series of random numbers, okay, which are coming as I'm using a random function from a uniform distribution from 0 and 1, and I'm generating 10 columns and 10 rows and 1 column of those data. So this is going to be a vector with a matrix with 10 rows and 1 column. It's going to be filled in randomly with numbers coming from the range of 0 and 1. And I'm going to subtract from each of those values the 0.5. So in principle, I should have half of the values being below 0 and half of them being above 0. And to check what's in so the average value should be around 0. Right, but it's going to vary depending on how many times I run this thing, and sometimes it's going to be a little bit less, sometimes it's going to be a little bit more. To check what's there for given run, we can set up an if statement. Okay, it starts with, as name implies, the word if, and then there's a condition going in that's checked. In this particular case, do I have 2 means? Well, I've got two means because I don't know why. One mean work fine. Well, it's probably left over of some sort. So I'm gonna just check if the mean value. No. Well, there's a reason why it's there, why it's there. Okay, let's investigate. Okay, so let's copy this piece of code and paste it here and see what we've got here. Okay, so our AU, as you can also see here, is a series of numbers. If you hover over, we're getting 10 rows, one column of numbers. Okay, we can print them here as a one column. This is, or if we want to make it print horizontally, we've got initially the vector that's one column, many rows. We can always say that we want to transpose the number with the prime, and this is gonna flip columns and rows. So this is gonna print as a series of numbers. So this is what we've got in our AU at this moment. If we calculate a mean of this, Control C, we're gonna get a single number. Yes, so if that's the case, we don't need it. So we don't need a second mean. Second mean would get us an average of one number, so it would return the same thing. So let's get rid of those means here and here. Okay, this simplifies things. So here we've got, going back to our initial if statement, here we're checking if the average value of AU elements in AU matrix is greater than 0. If yes, then the block following if is going to be executed. Only this piece of code will run. This is, as a reminder, a statement that prints our number in a supposedly nice way. The way it works is you specify a format. Oh, there's a question or something. No, nothing here. There's a first argument, which is a format string. It's essentially a string that's going to be printed out with the placeholders for the values we want to print. The placeholders are always composed of a % and one of the special letters. It could be either F for floating point numbers, E if you want to use exponential engineering notation, or D if you want to print integers. Okay, and then in between % and the letter, there might be numbers specifying how wide the field should be and how many decimal points. So here we can make it, let's say 6, and then 2 decimal points. Well, our range is between 0.5 and half, so let's make it 4 decimal points to have a more stuff there. Same thing here. 6, 4, hopefully not 1, 4, and the same thing here. 6 and 4, and for if the number is positive, I'm just printing this in front of it to denote that our mean is positive. Okay, and then after the format string, there's enough arguments to fill on all those placeholders. Here we've got one placeholder, so there's only one number provided, which is average of the numbers sitting in AU. And this piece of code is gonna be executed only if the condition here is fulfilled. If it's not, the MATLAB is gonna skip it and check another line of code. If it finds else if statement, it's gonna check another statement. So here it's gonna check if AU, the average of AU is less than 0. And if that's the case, it's gonna print out the values in a slightly different way. This time it's gonna put a brackets and minus in front instead of plus. It's gonna print a floating point number, but it's gonna flip the sign. So the number printed here is gonna be the same. It's gonna be always positive, no matter which of those two lines are used. But depending on the sign, we're gonna have it marked as a separate field preceding the number. And finally, if neither this condition is true nor that one is true, the code is gonna drop and check if there's an else statement. If there's else statement, then the last option is gonna be taken, and we're gonna print just the 0 with the 0 instead of plus minus in round brackets. So this is a very simple demonstration how conditional statements work. The one thing to notice is that they don't have to be that complicated. If we do have many more cases, sure, we can add another else if statement and another condition, but if not, we can just skip those things. Another common case is that inside one of those blocks we can put a nested, so-called nested conditional statement, and then we can check the conditions on multiple layers. So those things can get pretty complicated, but in the simplest case, it might be just two lines, one with the if statement and other one with the things that's got to be executed when condition is true. And we always end the block with end at the very end. If we run this code, and we're gonna see the output here, this is positive average. Okay, if we keep running this thing, as you see, the mean value changes because every time we run this snippet of code, the run function spits out a new set of random numbers from the 0 to 1 range. And depending on what the numbers were generated, we're gonna get either average being positive or negative, and the absolute value of this average is gonna vary from round to round. If there are only 10 data points, the changes can be quite significant. We're getting the differences of apparently close of about 0.1. But if we make the series much longer, let's say a few thousand points in a data series, we're gonna have 0. We're gonna be closer. We're gonna oscillate around 0 with much smaller amplitude, but we're still switching between positive and negative numbers. This is nearly guaranteed not to happen, because getting exactly 0 up to several decimal points is very unlikely. So we're practically never gonna get exactly 0 as the average. Okay, so that's how if statements look in a toy example. In the case of our function printing histograms, we can use it to decide if we want to overlay each histogram with the normal distribution plot or not. Okay, to do this thing, I've modified the hpanel function. I got to rename it to be distinct from the original one, so I just made it hpanel2. It takes the same arguments as before. Everything up to here is the same. This is the data in an array, the size of the grid, number of rows, columns, the positions in a position of the columns you want to plot, the height. There's additional argument and fit, which is assumed to be logical, so it's supposed to be either true or false. And depending if we set it one way or the other, the function is supposed to overlay histograms with the normal distribution plots. It's happening here. The modification of the function is very tiny. Most of the function looks the same. We did have to add another argument to the list of arguments. So this is where we specifying that we do or do not want to plot the extra stuff. Throughout here, everything is the same. There's no difference until we're done with plotting the histogram. Okay, this is the same as we've got here at the end. Those are exactly the same. This is exactly the same code, except that here we're done and we go through another pass to plot another histogram. In the modify function, we have an if statement. If n fit is set to true, which is supposed to mean yes, we do want to plot the normal distribution, we actually generate the average value and standard distribution for whatever column we're plotting at this very moment. We specify what's the step between the consecutive points on the curve we want to generate to plot. Okay, so this is splitting our range between lower and upper end of the X range into 250 or so points. Okay, and then we are holding on to our histogram that we just plotted here. If this was set to off, the histogram would go away, so you got to hold on. Okay, and then we are plotting. What you're plotting? We're plotting as X values the range from the X min to X max, and we're stepping by X step, which is gonna generate 256 or 255 points, I think, between X min and X max. So this is those are coordinates, X coordinates of the points along the line to plot, and the function norm PDF takes as an argument once more the same range as here. So it's gonna calculate the values of the distribution curve for the same values as we use as an X coordinate, and we want to use the average value and standard deviation that came from here. Okay, for plotting data that's been normalized, as you've seen before, to z-scores, it probably doesn't make much difference if those two values would be pretty close to 0 and 1, but for things that are different than the not normalized, calculating those two things for each series ensures that we see something. We're comparing something with a normal distribution that should look similar. Okay, so that's our function that's now able to plot the histograms. We can check if it really can. To do this, we go back to our main program. Okay, as a reminder, our modify modified function called hpanel2 to have to sit in a file named hpanel2. If not, MATLAB is not going to be able to find it. And once we've got it, and once we run this function here, we set nfit to false, so it should work as before. Let's see if that's the case. Control Enter. Here's our panel with nothing extra, just histograms. But if we specify nfit to be true, then you plot it. Now on top of the histograms, we do see in the red the normal distribution with the same width, same mean and standard deviation as the underlying histogram data. It clearly shows us that in most of the cases, the histograms don't look like a normal distribution. They are wider. You might guess why. Well, if you zoom into one of those panels, let's say this one, each of them do get their own icons to do things. We can zoom into this one, and you see there are data points here very far away from the mean or from the median, so they make the standard deviation look different, look bigger, right? They are stretching the normal distribution wider, so that's why it's wider than the bulk of the data. It's just demonstration that a few outliers that are they are probably coming not from a normal distribution might skew the overall parameters of the data to look like its standard deviation is larger than expected. So anyway, that's how we can modify our function to show or not the additional information. It can be modified even further by providing ways by means for simplifying manipulation of the panels and then changing the colors in a controlled way, or adding labels, adding titles. All of this is possible. It's just a matter of modifying this thing function further, adding additional attributes and modifying the resulting plot in this way. What can be done without modifying this function is using the value it returns. As you can see, it returns a pointer to our finger. Okay, and initially we're setting up the position, color, and the name of the panel by specifying it inside the function, but there's nothing wrong with taking this value. You can access it by getting it here, and here you can say HP, let's say HP what? Well, you can say, for example, HP name. Let's see, so we can say HP name, and we can set it to for histograms. Okay, and once we run it after our function returned us HP value, now once you run it, now whatever we specified as a name shows up here at the top of the window, and we can name, we can have more than one histogram like that. We can generate figure 2, 3, 4, and each one with a different title. So So this is probably the reason that it's those windows are not embeddable in the GUI, because you can have more than one. This is just one of many that can show up. So here's an example of functions and that combines a simple loop statement with a simple conditional to do things that to customize the graphical output that you might want to generate. Okay, let's see what's next. Okay, we will stop here once more, because from now we'll have to switch to finding data. So far we're blindly picking up one or two data sets to play with. We can try to find in a more informed way things that seems to be interesting, but to do this thing we wait until the break. So let's break once more. Okay, and I'll stop recording. Pause recording. Don't record. Okay, so now a little bit more complicated versions of conditional statements uses. First observation is that in principle, by combining for loops and conditional statements, you can you can find nearly anything you want in your data. You can identify subsets of data that you're interested in with no problem, except that it's gonna be very slow. As you've seen on the first day, the for loops are not that fast. It's much better to use built-in operations that are designed to be used for operations that should be performed in a very rapid way. And then there are essentially two of those functions or ways of employing conditional statements. The first one is a function called find. What it does is it takes as an argument a piece of data, typically a variable corresponding to either array or two-dimensional array, so matrix, and it's a conditional statement that it's going to be evaluated, in this particular case, for one column of our z-score matrix, z-score normalized data, and it's gonna find all the elements in this matrix that are smaller than -2. Okay, and what it returns is it returns the number of row, a list of the row numbers that correspond to data fulfilling this condition. Okay, if we want to check scan not the rows but columns, we can just change the way we pass the data to the find function. Here we're checking 500th row, but all columns, and we're checking if the values there are bigger than 1. If they are, then we're saving it in a call variable. So this is going to be variable holding the numbers of rows where the data is less than -2. This is the same, but for the columns. If we don't have to pick the section of the array, we can feed entire array there. Okay, and we can also combine conditions, so we can ask if there are any data points in our data array that are either smaller than -25 or the vertical bar corresponds to. I messed up. Okay, let's retype it. Let's retype it. Easy is less than -25 or easy is greater than 25. So we might look for data points that are either very small compared to the average deviation in our data sets or much bigger. That's right. The vertical bar is an OR operation. So if either this condition is true or that condition is true, the overall result would be true, and find is gonna find those things, and it is gonna return us a position within the easy variable where the condition is true. Even in case it's gonna work fine even in case of two-dimensional arrays, because the number it returns is gonna be it's gonna be a list of numbers. They correspond to something called linear index. This is gonna be a position in an array identified by counting first position going through the first row. Those are going to be positions 1, 2, 3 up to, let's say, position 10 corresponding to a 10th row. And then 11 is going to be the first position in the second row up to 20 if it's 10 row matrix. And then so this way you can identify position in the matrix using just a single number. So find is going to work either way. You don't have to worry that it's returning a single number and you've got a two-dimensional array with the position along the row and along the column. We can force it to return an array with rows and columns if needed. Instead of assigning the value of find to a single variable, we can make it return two values, two variables, or two arrays. The row array here is going to contain the list of rows, and the col array is going to correspond the list of corresponding positions in a column or at the intersection. There's an element that's fulfilling this condition. So this is how we can find positions of elements that are fulfilling some condition. Let's try to run it. We can uncomment this thing here. Let's see, so that it actually runs, and then I'm gonna put a block boundary here, so we run only this snippet of code. When you run it, I'm gonna comment this thing out. Here, 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 and here. Okay, so here we're gonna run this block here. Okay, now what do we have here? Okay, we now filled the index array. This is the one here. Here are the numbers. We can check how many we got by just asking for a size of int, and we did end up with 9 apparently. Okay, and here's another condition. Here we're checking for things that are as far away from the center of the the series from average of the series as possible. Here we're asking for things that are very close to the center. So this is what we've got in the row and column arrays. This is position along the row and corresponding position along the column where the data point is supposedly close to 0. And we can check that size of row, size of row is quite large. There's a lot of things sitting in between 0.10 and 10. But there should be equivalent number of positions in the core array. Yes, they're identical. And to find what's the value there, well, we can just ask what's in EZ at position, let's say row 1 and call 1. Okay, this is corresponding to the first element that's supposed to be close to 0. Is it close to 0? Yes, it is. It's fine. And what are the coordinates? What's position in the array? Well, it's row 1. So this is 7th row, and column is gonna be 1. So this is first column, 7th row. That's where our find statement found first element that's close to 0. Okay, so that's how you find things using find function. Okay, as you can see here, you're getting two types of information. One is you can retrieve the actual numbers by using the values returned by find, but you can also know what the positions were in your array, the elements are. Okay. Instead of generating the position in an array separately and then reading the values in a second step, we can combine those two things by just putting in find statement as argument inside the brackets or bracket for a given data structure. So those two statements are essentially equivalent. Here we do have the indices pre-calculated as in a separate step. Here the same indices are returned directly from find and passed to get the values of easy. So if we run this piece of code, okay, let's run it. And if we check what's in the easy25A, okay, well, there's a column. I don't want the column because it's hard to look, so I'm gonna transpose it and make it into rows. So here are the rows in easy25A. So this is those are the values retrieved using this statement. If we check what's in the other one, so this is gonna be 25B. They should be the same. Yes, they are indeed the same, no matter which version one use. And if we want to know what are the actual positions, then we do have position of those data points. For each of these data points, we can get a position by checking what's in the row and then in the column. at the corresponding site. If we care only about the values without paying attention to which position in the matrix they are coming from, we can use the logical statement directly when referring to our data array. Okay, and this is gonna return us the values. So in Easy25C, if we check, we've got the same values as before, right? Each number is the same. So the values are the same, but we don't know which position in an array they came from. In some cases, when we really don't care because you want to just get a sum of those or average value of those elements without looking into details, a function called the expression like this is going to be sufficient, and it's going to be faster than using the find to get the position of indices and then getting after values on your own. So depending on application, you might want to do use one version or the other. MATLAB is trying to remind you that using find in this context is slow by highlighting it and with this wiggly red line, and if you hover over, it tells you that if you want to perform better, then you might want to use logical indexing instead of find, and that's the name of the construct that you see here. This is the logical indexing, means that you use as an index into an array a logical statement that's gonna pull out the values that you're after. So for small arrays and small data sets, the difference might be not significant, but if you've got a lot of data and you've got to run through multiple rounds of data processing, those differences in speed would start to add up. So depending on what's needed, you're trying to use the most efficient way of performing calculations. And no matter which version you use here, it's gonna be way faster than if you were to write the loop statements to actually do the checks on your own. So one of the things that you should learn and get accustomed to when working with MATLAB is trying to find out situations that you can use built-in functions instead of looping on your own, because it's gonna be essentially faster than trying to write code in a conventional way, the way you tend to do those things in languages like Python or C or C++. It's slightly different way of thinking about writing programs. To you're after functions that are much more efficient than anything else. Okay. So that's how to find things in a simple way by going after the large or small values in a given piece of data. Here's another snippet of code that's trying to this time find genes that are not corresponding to highest value in our data set, but we're trying to find, let's say, genes that vary most in a given experiment. In general, if you have a set of observations made for a different for a different deletion mutants or whatever, different conditions. Okay, you're looking for genes. Once you measured the expression level of those, you're looking for genes that actually react to your to changes in conditions, to deletions of other genes. Those are things, those are observations that are most informative. They're going to tell you something about the relationships between the gene that you perturbed and those that change expression level. The bulk of the genes wouldn't care. They would vary a little bit. They will stay within whatever you see variation within a given data set, but there's a chance that few of those will be modified, will change expression, and those are the genes we're after. So here's an example of how to find those. Okay, so we'll starting with getting the variation of our expression data, but this time for each row. Each row corresponds to one of the genes and positions along the row for each individual column corresponds to different conditions. So we're looking how much expression of a given gene changes between experiments. Okay, this is done by looking at a standard deviation of the expression data, but instead of looking for variation within each column, we've got to change direction and go horizontally. So in a matrix, so to do this thing, there's a somewhat convoluted way of specifying it. First, we've got to specify how do we calculate standard deviation. It can be done either by dividing through the number of observations or number of observations less one. The difference is how the standard deviation is interpreted. This is coming from statistics, so we're not going to go into details, but we'll pick for in normal situations. We use n-1 weighting. This is in a case where our observations are a subset of entire possible set of data that can be generated. So to use it, I think we're supposed to use 1, I think, but I'm not sure. But it's no, default is 0, so default is 0, so this is gonna be n-1, so we'll leave it at 0, and then we've got to specify along which dimension we're supposed to get the averages or standard deviations. We want to go along, we want to get averages for the row, so we want to average along the columns, which are the second dimension, so that's why we use 2 here. Okay, and then once we've got, well, we can get those. Let's see, we can do Control-C, Control-V, and here's our variance of D. We can check what's there by either getting size here or checking ADV down here. Okay, so we've got 3,000 or so values. Yes, we're getting the standard. We're getting standard deviation for every gene. There's about 3,000 genes, so that's what we've got. Okay. Okay, so this is our standard deviation. Now, if we look at the first few values there, let's look at ADV from 1 to 10. Okay, and let's plot it as a column. So I transpose it. We do have the standard deviations varying from first, second, third, fourth, fifth, and so forth gene, but they are not ordered in any particular way. So we don't know which of those are largest, which of those are smallest. So to get after either smallest or largest numbers, we can just sort them. That's what we do here. Okay, and we now copy and paste here and run this. Now we've got ADVS here. It's the same size. The difference is that if we now look here into our sorted version of the matrix, now this is the smallest value, and then we're growing with the position to go. We're going to the largest values. The last few positions out there would be, we can say the last position would be end. That's special variable notifying the end of a variable. If we want to go, let's say, and see 10 positions at the end, we've got to back off to end minus 9, because both this value and this value is included, so we subtract only 9. And if we check there, and if we run in this snippet of code, now we've got the 10 largest values. So there's one with a standard deviation of 1, 9, and so forth. So note that this is for different direction, this is for averaging or looking at variation along each row. Is different than what we looked before, which was the variance and along for each column. Okay, so once we do have our sorted values of standard deviation, we can set our cutoff. We can decide what's the observations that will correspond to our top genes with the highest expression, or lowest if we check the other end of the sorted array of variance for each experiment. To do this thing, we just get the value corresponding to the value that if we check the averages, this is what we want to be higher than. Okay, so here's our cut. Okay, that's right, which we set to the value of the 10th best gene, and then what we do is we just find, and we're gonna find, oh darn it, what we're gonna do is we're gonna go back here. We're gonna find, we're gonna look through our data matrix. We're gonna calculate standard deviations as before for each row. That's right. And then we're gonna check if standard deviation for a given row is bigger or greater than or equal to our cutoff we set here. And if it is, then we're gonna get information about the row and position of the piece of data that's fulfilling our conditions. Okay, all we're interested in is actually the row, because we're after the rows with the high standard deviation. So all we're interested in is what's sitting in this row. Okay, and once we run it, okay, I'll comment this thing for a moment. Let's run this piece of code. Okay, control here. Okay, we're gonna get the row and column variables, and what's there? Here's our row, and we're getting 10 values, as you can hear. If you don't see it here, we can always say size of row, and we've got 10 rows, 1 column, 10 values. Those are the positions of rows that do have genes with a large variability when different genes are knocked out in a list. We can print the actual row numbers or transpose it, but this is uninformative. This tells us nothing until we know what are the actual genes that are corresponding to those rows. This is much better than saying, oh, gene number 64 in our table. That's right. To get the names of the genes, we can go back to the very beginning and look at our ET table. This is the table with the text data that came from our file. Just as a reminder, we can check what's there. Right, we can check what's in ET at, let's say, first 5 positions along the row and first 5 positions along the column direction. Okay, and what we see is we do have a column with systematic names. Then we've got the gene, the formal. Here's another case of a protein names that are or gene names, and then for the experiments we've got the header for each of the columns. What we want to do is we want to retrieve a name of a gene that's sitting at a certain position at certain row in our table with the expression data. Okay, we know what's the position of the row. How to check what's the name? Well, we can get to individual positions within our E table with the names by just using the proper position to specify the row and column. The thing to remember, though, is that if we use the numbers directly as they came here, where is it? As they came here, the position of the row is in a ED table is different than the row in our table with the labels. For the ED table, one position corresponds to what we've got here. That's right. This is not 1 in an array with the text. in array in a text position 1 1 is systematic name. It's just here. To get the top left corner of the data array, we've got to actually specify we want the second row and third column. That's right. That's how we're gonna get to row number 2, row number 2 and column number 3. This is the top left corner of our where is it, of where the numbers are. Okay, so to get the proper name, we've got to modify the row that we're interested in by saying that we're after, let's say, let's go back to our rows. Okay, this is, those are our row. Let's go this way. Oh, so let's, oh no, yeah. Let's make the window bigger so that it's not gonna wrap. It's gonna be better to look at, provided I don't have zoom on. Okay, so row, let's try what's in row once more, but transpose. Okay, so those are the rows that we're interested in. What is the, how to find the gene name for position 64 in a data table? Where we go, we got to do ET. We want to get this, get the row, we want to get row position 1. This is gonna return us 64, but this is gonna be one position off. This is gonna be one less than whatever we should specify to get to the proper sticker. So we're gonna get and add 1 to it. Okay, and we can return for now first and second column for our ET table, and let's see what's there. Okay, those are the two labels that were provided in the input file. So now we know that a gene with the descriptive name is actually one of the top 10 as far as how much changes you observe across the experiments in our data set. To get the next gene in a series, we can look for second index returned in the row array. So this is second gene found. This is another one. So those might be genes that are interesting for further analysis because they look way different than most of the other genes. So this is a simple way of finding those in a big data table. If you go through the code which was used to generate to find those, it's really short. This is essentially those few lines plus a line used to read the data file. So the script that's getting you identifies you the genes is really simple. So that's advantage of MATLAB, where you can do those things in barely any time in very few lines of code. Once we get those names, we might want to actually write them. We might actually, instead of checking by hand what's there, we can print those things out. Here's a very simple very simple loop here that's gonna do the job. Okay, we're essentially going through our row variable, which contains the positions of the rows that we're interested in. For each of those, we're gonna print out two things. That's right. There's one placeholder for a string, and there's another placeholder for a number. Okay. And what we're gonna print there? Well, we're gonna print whatever is in ET. I'm gonna mess it up so that you'll see why this extra stuff is needed. Okay, so this is our sticker taken from the text table with the names of genes, and here is recalculated standard deviation of the data in the same row. We're going along each row to get the standard deviation, and we do this thing for the 10 or so rows that are listed in here. If we run this thing, we're gonna fail. We're gonna fail because the fprint function expects a string when there's a placeholder with s here, and what's sitting here is not exactly a string. What's sitting there, we can check, and we've seen it before. If we did, let's say here, we're not getting a string, we're getting something strange. We're getting something called cell array, not a string. There's a little bit more about cell arrays in the PowerPoint slides from yesterday, so you can check the basic just rudimentary information about cells there. It's essentially a way of wrapping text into in a way that doesn't interfere with processing it as individual unit pieces of data within arrays. And to get it back into a format, into a version that fprintf is gonna take it, we've got to specify, as we had before, we've got to convert the cell array into a list of characters or a string. And once we do this, we can run the code, and now we're getting a printout with names of interesting genes and standard deviation. If we don't like what's in the column number 1, RET row. We can, well, this is getting us just, I think, the first column. So let's just, now we've got to add here row 1. We want the column. This is column 2. I think we need it here. Let's see. Yeah, here it's better. Apparently, with just one, yeah, it makes sense. With just one index provided as arguments to ET, if we provided just this, we are going down the rows, but along the first column in the array. This is this linear indexing I mentioned a moment before. If we want to get the second column, we've got to specify both row and column position. So that's what's happening here. This is our position along the rows, and this is second column. And now we're printing out systematic gene names and corresponding standard deviations for those things. As you've noticed, the numbers you see here are the same that we've seen somewhere here. Here, those are the same numbers. That's right. This is 7, 7. But the numbers here should be the same, at least. Yeah, it's 1, 7, 8, 5, 8. They should be. No, they are not. Ah, that's interesting. Oh yeah, because whatever. Oh yeah, because whatever we've got here is not sorted. That's right. The order of numbers here is the size, the magnitude of numbers increases to the right. The list here is not ordered by the expression by the standard deviations, ordered by the way the genes show up in our data table. So the numbers are the same, the group of numbers is the same, but it's sorted in different way. But otherwise we've got whatever we're interested in. Okay, if so, that's what we got here. If we want to store this list of genes in a permanent way, we can obviously, instead of printing to a screen, we can open a file as you've seen yesterday, and then use printf with additional argument corresponding to the file and write this thing to a text file. We can also take those genes and then plot them. Okay, we do have a list of rows corresponding to interesting genes that we're after. Okay, we can reuse our hpanel function, except that if we feed it with original data, the hpanel is gonna interpret our data as being column-wise, and it's going to print out series in the columns instead of series in the rows. That's what we're interested in. So one way to address the problem would be to rewrite the hpanel function to change it from selecting columns to print to draw the data, to make it actually plot series of data going along rows. But easier way is to just transpose our initial table. Now whatever was in the rows is going to be in columns and vice versa. So we flipped the columns with rows, and then we can use row position, and we're going to actually get whatever we're after. And here's the hpanel. Let's see if it works. Here. No transpose. There's no. Okay, this thing works, but I've got that typo here. Here. Error in W stream line 41 notes. What's in that? 41. I made a typo somewhere here. Go away. It's not clear to me what's the problem, but I can try once more. Clear the command. Let's go here, Control Enter. Well, this thing prints out fine. We've got 9 data sets with going 1, 2, 3, going horizontally through. It's not clear which gene is which, because we don't annotate those panels. So another way to make the panel printing function, panel drawing, the histogram drawing function better is is to accommodate the need for putting labels for each of those panels, so that you know which data set what we're looking at. So this would be another step in making our panel function better. Okay. But otherwise, we do have some insight into how expression for those genes is changing across different experiments. You can see that that those genes are different. That's right. In this case, you've got a few experiments where expression dropped down. Okay, in this case, it looks like there's not many cases where expression go down, but there are cases where things went up. Each of those genes is different. Apparently, they do different things in the cell, and they react in a different way to whatever the genes that we initially modified interact with the things that we're looking at. So this is sort of informative. What one would done next would be to look at experiments here, check what are the genes that correspond to those experiments. Are they in any way related to the gene that got perturbed, or vice versa? So that's the way of finding interesting things to work on from initial pile of several thousand of numbers that you don't know what to do with. So that's one way of using MATLAB for analyzing initial analysis of experimental data. It is disturbing. Why am I getting errors here? Okay, there is a error in H panel 19. Oh, I see what's the problem. You see, those errors are informative. What we see here is the subplot tells us that index exceeds the number of, yes, that's correct. The reason is this array is n position long, but we've got only nine panels. We've got 3 by 3 to solve the problem. What we can do is we can make this thing a little bit bigger. We can add, let's say, oh, let's add one more. Let's add one more row. Okay. And now when we run it, okay, we've got just 1, 2, 3. We've got 10 panels. There are 2 empty because we ask only for top 10 genes. So we could modify the cut we had before to generate to result in 12 values, and then 12 genes, and then we could make to finish up this panel. So but as you can see, after modification the error went away. We can get rid of the command window and rerun the code, and we're fine. So that's how to look at whatever we found in a visual way. Okay, and we're getting to a close. There is just one example I want to go through. So let's make another 5-minute break. And before that, Eloy asked me to show you this thing, and you are supposed, you kindly asked to evaluate me, so you can use this thing to with your cell phone to get there. Otherwise, I'm gonna come back in the next 5 minutes to finish to finish up before the link. I read all the QR code and go back to our last example for today. So the previous example was trying to show you how to get after genes that seem to react in the most pronounced way to across different experiments. We can also ask for experiments that generate a lot of genes that react to the change in a experimental conditions, say the deletion of one of a knockout of one of the genes. It's slightly different because we're asking for different set of genes. The actual question is, let's say we're looking we're interested in genes that are expressed at z-scores that are higher than 5. This is significantly more than the average variation within a given data set. So those are things that are outliers in a sense that they differ more than expected on average from bulk of the genes. The cutoff is pretty it's arbitrary. It can be set in as a parameter, and finding those genes is easy. We just use a find function to find all the genes, all the positions in our table where the value is greater than or equal than our count. Okay, and this returns us as before 2 columns. This is gonna return as a column with a row, an array with values corresponding to the rows where the outlier is, and corresponding position along the column is going to in a column is going to be reported as a call. If we look at the values in the call variable, we can look at them by just plotting a histogram. So let's make it a block here. Let's make a section break here, and let's run this snippet of code. If we run it, we're getting, let's move it, I'm fighting with Zoom. Okay, we're getting a histogram. Okay, along the x-axis are the individual values. So those are the columns that were found as containing data with above our cutoff. Okay, and then as a y value in the histogram is the number of times a given column number showed up in our data set. So as you can see, some experiments didn't show up at all. There are gaps somewhere here because there was no experiments that resulted in a significant change in that significant change in the gene expression. And there are other experiments somewhere here where there's a lot of experiments that a lot of genes that reacted to a given conditions. These experiments are going to be much more informative than experiments here. Here it doesn't care what we did to the gene. It's apparently this gene doesn't play any important role. Well, it's some piece of information there, but if we're interested in genes and finding relationship of those to what's else, what to other genes in a cell. Would like to find experiments where there's a lot of changes in expression. So those are the positions that are reporting large number of hits in a histogram. Here's one, here's another one, here's another one. How to find what those experiments are? Well, we've got to write a little bit more of the code. Okay, but not much. It turns out that MATLAB provides you a single function that will take a list of values as we've got in our call variable, and if we ask for two arrays returned by this function, we're gonna find one of them with containing the number of counts, and the second one is gonna give you the value that resulted in this. It is that number of counts. So if we check, well, let's break the code here. If we check what's in, let's say, well, first we've got to run it and help. Okay, let's run this piece of code. Okay, we should get the values here generated by group count. Okay, so now what's in CNT1? Okay, so this is 9 occurrences of whatever value is in val1, right? So it means for our first experiment, this is what it's here. Those are the positions of the experiments. We had 9 genes that changed expression more than corresponding, for which expression changed more than 5 times the average, 5 times z-score is higher than 5. At next position, we've got next value is, next count is 13, and this is for position number 2, and so forth. So we do know the number of counts for each experiment. How to find out what are the experiments with the highest number of counts? Well, we can just sort our count list, okay, and then this is what we're gonna have stored in here. So when we rerun it, that's what we've got here. If we look what in SCNT, and let's take first 10 positions. Well, those are the lowest numbers. If we want to get the highest numbers, we've got to do the same thing as before. We can say and minus 9 to end. Okay, to end. Okay, and this is so there's an experiment when there are 24 genes with z-score above 520, and there's another experiment with 21. So those are experiments, those are the counts for the most influential experiments corresponding to most influential genes. How to find those? Well, what we can do is Well, we'd have to find corresponding positions of the corresponding positions. We positions to the column numbers corresponding to those numbers. Okay, we can get them because they are sitting here. That's right. So if okay, let's ponder. Okay, let's see. So what we've got. That's what we've got here. Those are the highest counts. Okay. Well, so then it means if we try, okay, so let's try this. Let's try something like Q equals, let's find in our S count, in our unsorted count list. Let's find there, let's find in CNT. Okay, let's find there. Let's find their values that are higher than, and our cut is gonna be specified by SCNT, by SCNT of let's see. Well, let's first save this. Okay, this is gonna be okay. This is gonna be our. That's okay. Let's. Okay, let's get this one. Okay, let's get this. Control C, Control here. Control V. Okay, so now in Emacs, so those are the counts, the highest counts that we've got. Okay, we've got one experiment with 24 genes above our z-score cut, another data set with 21, 20. Okay, so let's try to find what those genes are. Well, if we look for values in the CNT column that are higher than 16, so let's look for CNT higher than 16, we should get index position in a CNT array that's corresponding, that's fulfilling, containing data containing those, fulfilling this condition. Okay, let's do find here. So those are positions 20, 25, and so forth in CNT. Okay, so those are positions here. We want to get the values in here to get the position of the row. Okay, so now we can either use find, or we can just, well, we can use find into val. Okay, so here we are getting now, if we flip it, here we're getting the rows in our original table corresponding to experiments with no, not row. We're getting experiments, we're getting columns in our initial table corresponding to experiments with the largest number of genes, increasing expression by higher than the cutoff. Okay, so this is what we can now save somewhere. Okay, let's save it. Let's save it. Let's save it as a, let's say let's see, let's call it, well, okay, so what did I do so far? I see. Okay, so I want this, Control C, and I want to so we were here. Okay. Well, I'm gonna put it here. Okay, so this is gonna be my list of okay, let's call it this. Okay, let's save it here. Okay, and now once we've got the position of experiments, then we can get the names of those by looking at ET. Okay, we're looking at the first row in ET. This is the header in our text table, in our initial data table. We're gonna look for what's in exp1, but we want to add 2 because the first 2 columns are with the text, so we want to start with the third column, so we gonna do +2. Okay, and if we run this piece of code, Control Enter, I want to remove the semicolon and then rerun it. So those are presumably genes that, well, we got to count. See, we had initially here 16 as the lowest value, but if we do condition with greater, then we're gonna skip those. So we're gonna have 1, 2, 3, 4, 5. We're gonna have only those. So if we look for 6, we set condition to equal, greater than, or equal here, and then we rerun it once more. Now we're getting 11. There was another experiment that had 16 genes that had 16 genes above cutoff of 5Z. So those are our genes. Okay, we can save it somewhere here as the and those are genes that were knocked out. Those are experiments. Name. Okay. And then if we want to see what's there, we can try to plot histograms for those. How to do it? I'm gonna steal what I've got here. Control C. I'm gonna paste it back here, and I want to plot data from EZ. Okay, I've got 11, so 3 by 3 matrix is not, so I'm gonna make it 4 columns wide. And I want to have experiments with positions here in X1, so I just say X1 here. Okay, and those are different experiments. Yeah, so that's what we want to plot. Let's see, what do we have? Okay, here we go. Yeah, so that's what we've got. We've got 11 panels. Okay, and we are presumably finding experiments with a large number of observations above z-score of 5. So it means that there should be things somewhere here in each of those panels. We can check the first one and see if there's anything here. Hopefully there's something. Yes, they are. As you can see, there's quite a few of experiments sitting above 5, and this is what we're after. We're after data sets with a lot of genes showing up here, So it looks like we've pulled out roughly the right stuff. I would look more into this thing to convince myself that I'm getting the right data, but I think this approach does work. So the idea is that if you start asking very concrete questions and asking for subsets of data in a very concrete way, you can come up with a piece of code that's gonna find you things in literally few lines. Here's a slightly different question, and the answer is found in literally few lines of code. This is maybe a 10 lines of code. So in this sense, MATLAB is very, very efficient. You can get answers to questions that might involve pretty complicated and pretty lengthy computations, but in MATLAB the code is very, very short. It's just a matter of thinking how to write it to get to the right answer. And in most of the cases, it just is a sequence of operations. Like here, you don't have to think about writing loops and conditional statements and for blocks. Its code is much simpler than in conventional languages. So that's about it, I think, for us. Hopefully you found the class useful and informative. The only way to get to learn about MATLAB is start using it. So it's just a matter of practice. It's not too complicated. It's nice because you don't have to have your experimental data. You can start generating data using those simple ways you've seen. I've been using throughout the class, and then you can try to see if you can extract the right things, analyze this synthetic data in a way you want to. If you can show it, plot it in a proper way, it's just a matter of practice. Otherwise, thank you very much for patience and participation. I'm gonna now stop recording. Yes.